Welcome back for another Minitab session. This time we're going to take a look at hypothesis testing. And in this video, what we're going to try to do is understand different types of hypothesis testing and what is actually going on in terms of the interpretation of the graphical output as well as the interpretation of the analytic output or the text format data that's in the Minitab session window. And what we'll also try to do is understand how do we present these types of graphics to management so they don't get confused by the graphical output. So let's go to Minitab. We have a data set called hypothesis. And we'll see that in there are a number of different types of tests that we can use to illustrate how to do this type of work. What you see is the opening screen when we open up this hypothesis testing Minitab file. And there's 7 different things we're going to take a look at. So we'll take a look at one sample t-test, and this would be like short-term data or a small sample size versus a target or a goal. And so for us, that'll be C1 versus a target. We'll take a look at the one sample z-test, which is longer-term sample, or a sample size is greater than 30, versus a specification, which for us will be C2 column data versus a target. Two variances test, which is taking a look at the difference between two samples. And here we'll look at columns C3 versus C4. We'll take a look at a one variance test, where you have a variance versus a controlled range or a specified variance. And so we see here we can take a look at C1 and C2 versus the specified variance. And then the two sample t-test is new short-term data versus old short-term data. So we're comparing like a before and after situation, or two data points that are observed at the same point in time. Two variance tests is taking a look at new short-term versus old short-term variances for consistency of performance. And the test of equal variance is doing a similar thing when we have the data in a column that's stacked, and we have identifiers in one column where the factor names are. So here that's C5, and then the data related to that is in C6. What we want to do for each of these is try to figure out how do we do the test, how do we interpret the textual and graphical results, and then how would we want to modify those with respect to management. So our first test that we want to take a look at is a one sample t-test, and here we're going to see the historical mean for this data in column C1 is 0.545. And so what we will do is we will go up to stat, and in this we see basic statistics, and here's where we see all of the different samples, and we come down here to one sample t-test, and so we will click on the one sample t-test, and this gives us this window. So we have one or more samples each in an individual column, which is what we'd like to have. We click in here, and we see one sample 20, so that's a sample size of 20 in column C1. We're going to perform a hypothesis test, so we click on this box, and then the historical mean is 0.545. Okay, so those are all the inputs that we would put in this first window. Under options, we see that we can select the confidence level, so we'll always be using 95%. And the alternative hypothesis is the mean is not equal to the hypothesized mean, or we can select a two-tailed test. Here the mean is less than, or the mean is greater than the hypothesized mean. Well, I don't know which direction it is or anything about this. So what we're going to stick with is this is equal to, is not equal to. Okay, so we select this, click OK. Graphs available to us. We can take a look at a histogram, an individual value plot, or a box plot. And when we have a small sample like this, it's best to use both the individual value plot and the box plot. Histograms are not very informative, and as a matter of fact, they're a little distorting, so we'll leave those alone. So we click OK, and now we click OK. And so what we get then are two different outputs, okay, and they tell us pretty much the same thing. As we see here, we have our two sample 20. Here is the mean, and this is the sample mean based on the population. So the target is included within this line, both on the box plot and on the individual value plot. Now, what I would do for management is deselect this individual value plot. That's helpful for an analyst, but it's not so helpful for management. Here we see a summary of what the distribution is, even though it's for 20. And so as we're looking at this, this is a good way to take a look at this. Now, what's okay is we have some sort of sample here. Now, I probably should double click on this or right click and say I should edit that label. Okay. And the reason I want to edit that label is one sample 20 was nice for me as an analyst, but it doesn't tell anything to management. So if I'm taking a look at this, I actually have some sort of name here for this factor. So I'm going to just call this analytical factor. And so this is what we are analyzing. Sorry for me, I am actually working on an apple and I have no love for apples. Okay. So this is one thing we would want to change. Then we come up here and so we see this H sub 0, 95% confidence interval T. If we right click on this for the subtitle, we probably want to just eliminate this. Because, you know, management doesn't really need to know all that. We can say that to them, but then that can just raise extra questions that they have. And then we can right click here and say, okay, let's edit this title. And it's a box plot of analytical factor. So if this was for cycle time, we would say cycle time for a process and so forth. Then we have this information here that tells us what is the population mean or the sample mean, and then what is the population. As long as this H sub 0 is within this line, then we would say that there is no statistical difference. So now I'm going to move this down to a smaller level. Let's take a look at what we got in the session window. So in the session window, we see that we have this test of is mean equal to this or not equal to this. So that gives us the hypothesis. We have the variable, the sample size, the sample mean as calculated from the data, the standard deviation. This is the standard error of the mean. That's S over the square root of M. And then we have the confidence interval. And so what we see is that the p-value is 0.121. And so we're going to reject the null hypothesis that there's a difference because we see that the population, the sample size and the population estimate are overlapping. So this is what we get with a one sample t-test. Now we can do also a one sample z-test, and this is when we have a sample that is greater than 30. Okay. So again, we go to stat, basic stat, one sample z-test. Okay. Now this is for the normal distribution. Okay. So we do indeed have one sample in one or more columns. So I labeled this one sample 40, so we'd know the difference if this is greater than 30. Do we have a known standard deviation? Well, we're going to say yes, we do. So I'm going to say 0.01 is the known standard deviation. We want to perform a hypothesis test. And so the hypothesis test, this mean, is equal to 0.545. Okay, so this is similar data to the first sample, but we have more of it. And then we take a look at the options. So we're going to keep the options exactly the same as with the one sample t-test. So click OK. And then the graphs, we'll take a look at exactly the same graphs. Okay, and so let's take a look at the individual value plot and the box plots. Now when we have a sample size of 40, I really don't need to take a look at the individual value plots, but I want to show this to you just so you can make that judgment for yourself. Okay, and then we click OK. So here we get the two outputs again. Okay. Now, if we take a look at this first one, the individual value plot, Minitab does something a little strange. There's no scale in this direction here, but Minitab is placing these dots above each other. This is a graphical process called kerning, and what they're doing is they're saying there's more than one estimate at that data point. Matter of fact, there's lots of them. And again, here we see H sub O is right within that same distribution. So we're going to have the same type of conclusion that we draw with a small sample size. And so I'm going to, again, reduce this in size. Now let's take a look at the box plot. And again, we see the same result, and we'd want to do the same thing. So the same edits we would have on the last one we'll have. I won't do them so we don't make this video too long, but we would do exactly the same thing as we had on the last one. And it's actually the same data, but it's a larger sample size. So that's good, we're getting the same conclusion. And then if we take a look at the window, we see, oh, here we are. Sample size is 40, okay? And what happens is as sample size goes up, the confidence interval shrinks, so the confidence interval has gotten smaller, and the p-value now is approaching 0.05. So it's close to becoming statistically significant, but it's still not statistically significant. So we draw the same conclusion that we had from the sample size of 20, okay? So these are the two sort of different ways we take a look at it. The biggest difference is that if we're having the sample size less than 30, it's one sample t-test. If it's greater than 30, it's a one sample z-test. Okay. Now let's take a look up at the other test we'd like to do. So we've done the first two. And so now we'd like to take a look at two variances. Okay. And the two variance test here is going to be taking a look at the differences between two samples in C3 and C4. Okay, so we go again to stat, basic stat, and then we come down here and we see two variances. Okay, so two variances, the samples are in, and we're going to see different columns. So each sample in its own column. Sample 1 is going to be sample A. Sample 2 is sample B. Okay. And then we take a look at the options. And again here we're saying, okay, what I would say is I want to take a look at the ratio between the two. So ratio standard deviation 1 to standard deviation 2. So that's one choice. Or I could take a look at sample variance 1 to 2. And so that's another choice. And then I can take a look at confidence intervals, hypothesized ratio, and then ratio, is it equal to the hypothesized ratio? So if they're 1, the ratio is then equal. So it will be a test of equal variance. So we can say, okay, let's take a look at this. We'll say yes. And then for graphs, we can take a look at summary plot, histogram, and individual value plot. So let's look at the summary plot and the individual value plot. And for results, we can take a look at all of these types of things for the two sample t-test. Since these are all the standard set of results, we'll just look at them. Okay, so here we see this two samples individuals plots, and we can clearly see there's a big difference between the two plots, between sample 1 and sample 2 in terms of the variance. And here we see the two, and we're seeing the same difference here. Now the question is the data normal or is it not normal? So if it's normal, we would take a look at Bartlett's test. If it's not normal, it's Levine's test. And we take a look at the data, and one of the things we'll see is that we do not think this is normal data. How do we check that? Well, we can come and take a look at graph, probability plot, and take a look at this in terms of multiple because we have two distributions. And so the graph variables are A and B. Okay, and multiple graphs, and I'm going to overlay them on the same graph so we can see what they look like. Okay, and we click OK and OK. And what we see is here are the two variables, and we see that neither of them are actually a p-value of less than 0.05. So we wouldn't reject either of them for normality. So we would see that both of these plots are falling within these normal confidence intervals, but we see that there's a very different shape and a very different overlap of the statistics. So we're going to expect to see a big difference in the two when we look at the data. So let's take a look then at the data that we get out of this chart here. Oops. This is the two variances, so we're seeing that there is a big difference here in the data. Okay, and here we come back. So we end up taking a look and we say, okay, the p-value is 0.09 or 1.27, so neither of them are normal. Okay, and we take a look at the differences here, and the difference is the ratios. And again, when the ratios are equal to 1, then we would say that they're equal. So we see the standard deviations of the ratios, and we say, okay, here's the ratio range for the variance ratio. And we see there's a very big difference in the tail of this on Levene's test. Okay, so this is one way of taking a look at the variance. Now, there are other ways to take a look at the variance. So let's come back up here. We could do a one variance test. So here I could do C1, C2 versus some sort of controlled or specified variance. Okay, so we'd then be asking, is there a difference between the variance in this sample and the variance that we may have specified for that particular data? And again, we go back here, stat, and we come down here to basic statistics. And now we have this one variance test. And so we have one or more variance samples in each column. So we have sample 1, perform the hypothesis test. The hypothesized standard deviation is going to be 0.01. Okay. Under options, we can just take a look at this. Do we want that standard deviation or not at a 95% confidence interval? So we select OK and OK, and that's all we have to do. And so what we see is the p-value is here, and so it's statistically significant that it's different from 0.01. Okay. So again, we can start understanding something about this. Now I could be using here a specification or a target or a range that we'd like to see for performance for the consistency of the process as a standard deviation for this type of test. Now the next type of hypothesis test I'd like to illustrate is, so we've done the two variance test, we've done the one variance, is a two sample t-test. So here what I'm going to do is I'm going to take a look at samples A and B and see what is the difference in the averages of those two. Was there a difference in the change of performance between when A and B were actually conducted as tests? So again, we can go up here to stat, and here we go basic stat. So all of these are where we find the tests. Two sample t-test. Now I want to note there is no two sample z-test. They're only for small sample size. Okay, so this is one thing just to remind yourself. You might find that as a quiz question later on. Whoops, I'm not supposed to give away those secrets. Okay, so the samples are in one column. No, they're not. What we see is the samples, each sample has its own column. So sample 1 is sample A. Sample 2 is sample B. The options are going to be what we've selected before. The difference is 0. That means there is no difference. Okay. And the graph we're going to take a look at is, let's look at both the individual's value plot and the box plot. And then we click OK. So again, we see these two outputs. Now what's different is, notice on the individual values plot that we've actually got a line connecting the two. This line is going to be called the main effects plot line. And what it's showing is the difference between the two means. So hypothesis testing is indeed a difference between the two means. When it's got a slant like this, or it comes at an angle, it means that there's usually a statistically significant difference between the two. Now again, we want to get management accustomed to looking at this type of plot here. And so let's take a look at the box plot version. Now here in the box plot, what we see is 50% of the data is in the box, 25% is up there, 25% is down here. And so that means 75% of this data is down here, 75% is up there. That means there is a statistically significant difference between the two. So just graphically we can see this. Again, what I want to do is change some of these labels. So for management, here we would change data to the name of the data. We would then say, what is the rational subgroup represented by sample A? What is the name of the rational subgroup represented by sample B? And this is a box plot of differences, sample A, sample B. So we can again change those names so management can very clearly understand what's happening. So let's take a look at what happened here in the Minitab output. So here we see the name of the test, the two different samples. We see the means of the two, the standard deviations of the two, and the standard errors of the mean. And we see that there's a very big difference in standard deviation for sample 1 compared to sample 2. Sample 2, or sample B rather, has a smaller mean. And we take a look at this and the p-value is highly significant, 0.001. And so we would say, yes, we would draw the conclusion that there is a statistically significant difference between sample A and B. So if this sample was taken before test and after test, and the rule of interpreting this data is smaller is better, and so we would say like this is defect level, we would say that then we have clear evidence that sample B is indeed superior to sample A, and it is statistically significant. Okay, so let's come back up, and we have, I think, a couple more of these examples or illustrations to use. And so now we've seen, okay, the two sample t-tests. We could also take a look at two sample variances, or the two variance test. Now this is going to be a little bit different than what we had seen before. And so when we take a look at these variance tests, we see we have the two variance tests here in Minitab under the basic stats, but also we have another one under ANOVA where we have a test of equal variance. Okay, so let's take a look at what those two differences are. So under basic stat, two variance test, we select this and we have the two variances, and this is the one we did before. Okay, so we're just going to select the OK. We'll get the same results out. We'll take a look at this. So, okay, we get this difference, and we do see that there is some unique differences between the two. Now we saw a little bit more clearly the differences in the mean and the standard deviations when we did the two sample t-test. Okay, so now let's take a look at the test of equal variance for the same ones. So that is under stat ANOVA, okay, test of equal variance. Now what we see here is the data are going to be presented in a different way. Okay, so response data is in one column for all factor levels. And so what we see is this is actually true because we stack the data from samples A and B, and that's in number 16, column 6 rather. Now the other choices here are data are in separate columns for each factor level. Well, they're not. So here we're going to select this one. So the response data is in the stack data, and the factors are where we have the labels which identify which are data A and data B, or samples A and B. Now the options here, again, we can take a look at this data here. We can use tests based on the normal distribution. We come and take a look at graphs, and we can take a look at individual value plots and box plots again, as well as summary data. The results, we will just take a look at the confidence intervals of tests, okay. We can store the data for the output, but we're not going to do that. So we'll just click OK. And now we get three different types of output. So we get the histogram, and we get the individual value plots, and we get the test for equal variance. Now, did you just notice something? We got all three of the tests when we did this. And the reason is that this is actually doing an analysis of variance. It's giving us a more complete type of analysis because we're looking at both mean and standard deviation at the same time. So the test for equal variance may actually be a more productive test for you to use because you don't have to do as many different individual hypothesis tests. So as we're taking a look at this data again, and we take a look here, we can see in the window, in the session window, that we get exactly the same type of information. And we can see the individual confidence level of what we see. And we see the test and the methods that we have here. And it's an F-test, and the p-value is, yes, they are statistically significant. 0.028 is much less than 0.05. So again, this is a nice way to go and summarize all of the different hypothesis tests that we have. So let me just go back and review where we were in terms of what's happening here. And so we've now done the 7 different tests. We've learned how to do the test, and you can follow then and practice in Minitab on these sessions with the file. We've learned how to interpret them, and also then how to simplify and present the results to management. So why don't you go try and do it yourself? Now we've seen from hypothesis testing the value of this in terms of making some estimates. We also noticed that we were using this with the sample me data to understand, is there a difference between populations and samples? Now we'll see in the real world, we very rarely will use this in terms of data probing.
We'll use the logic of hypothesis testing very often in the advanced statistical tools. And we'll probably use this two-sample t-test to understand, is there a difference that's statistically valid between the beginning and the ending of our project? So those are things that we will find very, very helpful in the future. Some of these other statistical tools will find that our processes actually are getting more complex than just taking a look at this simple one-factor type of analysis. And we have much more complexity that we'd like to engage. So let's turn to taking a look at some of these more advanced statistical tools now.